All right, guys, welcome back to our chapter 2 in our Chem 20. This chapter is on measurements. Well, measurements and problem solving. So, to get started, we need to first talk a little bit about what uncertainty is. Then, we're going to touch up a little bit on scientific notation, just real quick. Then, I'll show you guys how we report scientific notation, like standard. And then how we start looking at sig figs. We'll do some sig fig calculations, how we make measurements, what the measurement units are. So that's what this chapter is full of. And then I think it'll end with a little bit of problem solving, meaning that we're going to do some unit conversions and possibly talk about density. So uncertainty is indicated by the last reported digit. So let me give you an example. Let's say that average global temperatures have risen by 0.6 degrees Celsius in the last century. So from, I don't know, 1920 to 2020, this is average. So X bar is average. Average global temperatures, we'll call it GT. Average global temperatures have risen by 0.6 degrees. Now, by reporting reporting a temperature increase of 0.6 degrees Celsius, what the scientist means is that it's 0.06 plus or minus 0.1 degrees Celsius. Because that last digit that's reported is what we call the last digit of uncertainty. If they were more certain about more digits, they would have put more digits. So the temperature could be as high as 0.7 or it could be as little as 0.5, but it's not going to be 1 degree Celsius. It won't, it won't be that much in terms of the difference. So the degree of certainty in this particular measurement is critical. It may, if this is the temperature of the global, global temperature, this could influence, like, let's say, political decisions, right, that directly affect people's lives. So having this kind of information is and the more accurate it is, or the more what's the word, precise, the better. We're going to have to talk a little bit about accuracy and precision as well, so that you guys can kind of define those and know the differences. So first, let's talk a little bit about scientific notation. Now, scientific notation has two parts. There's the decimal part. This is the number part that's between 1 and 10, and I'm going to emphasize that. It's going to be between 1 and 10. Don't write scientific notation numbers that start with 22.1 times 10 to the 1, right? This number right here is not between 1 and 10. So keep it between 1 and 10. Change the color up. Maybe that's a bad idea. Man. Okay. The exponent part, that's the other part. Exponent part is 10 raised to an exponent. Here the exponent can be n. Now, n, you can see, can have different units. It can be positive units or it can be negative units. Now, a positive exponent means that it's a 1 multiplied by 10 n times. So n being the number that's in there. So if it's a 0, anything multiplied by 0 in this case, or 1 times 10 times 0 would still just be 1. 1 times 10, we always say 1 times 10 to the 1. Right, this is the number part. It can either be 1 or it can be something between 1 and 10. Would be 10 times 10. I'm sorry, 10 times 1. So just 10. 10 to the 2 is a 1 times 10 times 10, so 2 tens. So the 1 part you can often just kind of not think about. It's just 10 times 10 for the 10 to the 2. It's just 10 times 10 times 10 to the 10 to the 3. And so this is a way of representing big numbers. Like if I have a really big number, like 1,967,000, something like that. Let's just say it's even bigger. Let's say it's 1 billion. I don't want to write 1 billion. I want to write something a little shorter. I could write that. 10 to the 9 just means that it's 1.96 times 10 times 10 times 10 times 10, right? 9 times. Okay, so 10 with a negative exponent is like saying 1 divided by 10. And so if it's a negative 1, you're only putting a 1 over 10 one time. If it's a negative 2, it's 1 over 10 times 10. So it's just the inverse. It's the inverse. Now, how do we convert between scientific notation and a number, or let's say a number to scientific notation? So you find the decimal part, you find the exponent, and then you move the decimal point to obtain the number between 1 and 10. So let's see. So you would find the decimal. That's normally where a decimal goes at the end of a number. Then we move it over. So 1, 2, 3 places, so that now it's going to have a number between 1 and 10. This is the number 5. And then we moved over 3 places, and so we're going to raise 10 to the power of 3, because we moved 3 places. If the decimal place is moved to the left, then the exponent is positive. So in this case, it moved to the left, so it's positive. If the decimal point is moved to the right, the exponent will be negative. So for this number here, we want to make the number part between 1 and 10. So we got to move this decimal point over 4 times, so that now we can write 3.4, which is between 1 and 10. And then because we moved it to the right 4 places, 10 to the minus 4. Hopefully this is not going to be a struggle for any of you to do this. Okay, and so that is moving a number into scientific notation. Now, of course, you got to be able to move a number out of scientific notation as well, and that involves the reverse, at least the reverse direction of how you moved the decimal. Just remember it this way. If there's a negative number, then this is a small number. This is less than 1, and that is telling you how many, it's not telling you how many zeros are going to be in front of your number, but it tells you how many, you can imagine that there's going to be, zeros in front of your number. It actually ends up being 4 in this one, but this number doesn't always have to be a 0. And then if it's a positive, just know that means it's a big number, and that this is actually much bigger than what you're looking at. Okay, let's talk a little bit about reporting scientific numbers. So we always report what we would consider to be certain numbers and then an estimated number. So in this example, the first 4 digits are certain, and so then the last one is estimated. Now, how do we know how many certain numbers there are in a measurement? Well, that depends on the measuring device. The greater the precision of the measurement, the greater the number of sig figs, we call it. All of these are the significant figures that we could keep. So let's get into that. So here are some examples. Let's estimate tenths of a gram. So this balance on the left has markings every 1 gram. Now we estimate to the tenths place. So to estimate between the markings, we got to mentally divide the spaces into 10 equal spaces and estimate the last digit. So what I can see, looking at where this red line is that, well, I have to make up some information also, right? Because I got to fill in the numbers here. I know this line is 0, and I know this line right here is 10. I see that there's a big line in the middle. That must be 5. I then know all of these little lines are 1s. So it's over the 1 line, but it's not quite at the 2 line. So I know it's 1 and something. So I'm going to say it's a 1 for sure, and then I'm going to estimate that it's a 0.2. Now your book says, 1.2. I might say 1.3. Doesn't matter. When you're putting that estimate, everybody's going to have a different eye, and they're going to see a different thing. Grams, because these are grams, we'll get into that later. So for this device, we could only get 2 significant figures from this, a certain number and an estimated number. Now this next scale here on the right actually has markings for every tenth of a gram. This one on the left didn't. This one on the left had markings for every gram, but not anything in the middle. So this one's a little bit better of a scale. So we can see here's the line we're going for, right here. That it's past the 1 It's actually past the 1.1, the 1.2, but it's in between the 1.2 and the 1.3. So we know that it's 1.2 and then something. So that's where we can estimate. Now I might say 1.25, you might say 1.26. We can't say 1.256 and make it even more of an estimate, right? We only get one estimated number. So that's why this marking or this device would give us an answer, a measurement that has 3 significant figures. 2 estimated and 2 certain and 1 estimated. Okay, let's talk about significant figures. I've been saying it for the last 2 slides. Let's talk about it. So all non-zero digits are significant. So that's one rule that you can just remember. All non-zero digits. All interior zeros that are zeros between 2 numbers, these are also significant. I'll show you, I'll give you some examples of each. So like here are 2 sets of numbers that are both non-zeros. So the first set would have 3 sig figs, the second would have 6 sig figs. Now all interior zeros, so 101 or 10,001. These are interior zeros between significant figures, so all of these are also significant. So this would have 3 sig figs, this one would have 5 sig figs. Now trailing zeros, these are zeros to the right of a non-zero number that fall after a decimal point. So this would be like this number or this number. This is a significant number. These are significant numbers, and therefore all of the internal zeros are significant numbers. And this is a trailing zero. Now, these trailing zeros are after a decimal point, so they are significant. This trailing zero is before a decimal point. This is the number 100. It doesn't have a decimal point. It's a trailing zero. It should have, these are the worst kind of numbers. These are what we call ambiguous. This is an ambiguous number, and ambiguous numbers are not significant. So while this number here would have 1, 2, 3, 4, 5, 6 significant figures in it, this number here, well, we'll get back to this one. We haven't talked about the last rule for that one yet. This one would have 2. But this guy would just have 1 sig fig. Because of these, this is a trailing zero, so it's non-significant. That makes this zero not an interior zero. It's a trailing zero as well. And so then it only has 1 significant figure. Leading zeros, that's the last rule. Leading zeros are not significant. They only serve to locate the decimal point. So that's the whole point of these 2 zeros right here, is that they just help us know where the decimal point is. They are non-significant. So 0.000003100 would have 4 sig figs. None of these count. And then the 3100, these are trailing zeros after a decimal point, so they count. All right, so pause the video, try these numbers here, and then we'll do them, or then unpause it because I'm going to tell you the answers right now. So this one has 2 sig figs. This one has 4 sig figs. This one has 4 sig figs. This one has 3 sig figs. This one has, skipping one, 5 sig figs. This one's ambiguous. And I'm hoping you read the chapter, because if you didn't read the chapter, at this point, you wouldn't know that this one has infinite sig figs, or unlimited sig figs. This is not 2 sig figs. So let's talk about that real quick. So exact numbers have an unlimited number of sig figs. Okay, think about that. How many humans are you, right? You're 1 human, right? Are you 1 or are you 1.1 human? That's a little more accurate. Are you 1.0000 humans? I said 1.1. I meant 1.0. Are you 1.00000000 humans, right? These are all the same number. And you can see that you can go infinitely out and still be at the same number. It just is more precise, right? But for counting, it doesn't make sense. So exact numbers, we just say they have an infinite number of sig figs. We don't even talk about them. This is true also of defined quantities. So for example, we say that there is in 1 inch, there is 2.54 centimeters. This is a conversion that is a defined truth. This is not something that is an estimation where we say, it's close to that. This is exactly this would also have an infinite number of sig figs. We wouldn't talk about this as being 1 sig fig or this being 3 sig figs. Okay. Let's talk about some rules for rounding, and then let's do some calculations. So when numbers are used in calculations, we do want to round to reflect the significant figures. We don't round in the middle of a calculation, we round at the end, and we only round the last number. Normal rounding rules, if it's 5 or more, then we round up. If it's 4 or less, we don't. We round down, or we just drop the next digit. Okay, so let's talk about calculations. There's the multiplication and division rule. The result of a multiplication or division carries the same number of sig figs as the factor with the fewest sig figs. This just means as the number in the calculation with the fewest sig figs. So, for example, in the top equation here, we've got a 3 sig fig number, 5.02, a 5 sig fig number, a 2 sig fig number, all multiplied together. Now, when you do these, I don't recommend doing them in slow steps. Put all those numbers in your calculator, get the answer, write the answer down. And then do it again to make sure that you didn't make a mistake and that you get the same number. You should always do that. Never count on your first. I've been doing calculations longer than you've been doing calculations, and I make calculation errors all the time because my calculator has a number in it or I push a button. Just do it twice. But once you have your number, then worry about the sig figs. Okay? So we know this answer is 45.0118. Now we don't know how many sig figs we can keep. The rule says for multiplication and division problems, whichever factor, in this case this number, has the least number of sig figs, so does your answer. So this is 2 sig figs, right? Trailing 0. So our answer can have 2 sig figs. Now we look at this answer and we say, where are my 2 sig figs going to be? It's going to be 4 and 5. Is the 5 going to get rounded up by this number? No, it's a 0, so 45. Division, the same thing. 4 sig figs and 3 sig figs, we just get the answer. We say, okay, 3 sig figs is the smaller number. We got to round this to 3 sig figs. So 9, 6, 5. Is our 5 going to stay a 5? We look at the next number, it's a 9. Okay, we can round up. So 0.966 is the number. So that's the multiplication and division rule. There's an addition and subtraction rule. This one's different. In addition or subtraction, the result carries the same number of decimal places as the quantity carrying the fewest decimal places. So here we don't care how many sig figs are in each number. We want to know where is their decimal places. So the easiest thing you can do is to line up all your numbers, and this is particularly difficult when you get a bunch of numbers in scientific notation. Let me give you an example of that. 4.32 times 10 to the minus 1 plus 1.66 times 10 to the 3 plus 1.2 times 10 to the minus 5, right? I'll come back to that in a second. So what we want to do is we want to line up all our numbers, all of the decimal places in a row, right? So that we can see how many decimal places each number has. This one has 2, this one has 3, this one has 3. So our top number only has 2, so our answer can only have 2. And so that's what we do. We draw a line right after it, and we cut off everything that's beyond that line. So 9.21 becomes 9.214, becomes 9.21. Okay, back over to the up here. Now, when you have numbers in scientific notation, it looks like all of these numbers. In fact, it looks like this number right here only has one decimal place, right? One place past the decimal. But this number is actually 0.00002. That's what 1 times 2 10 to the minus 5 is. So this number actually has 5 decimal places. So misleading, right? So whenever you get numbers in scientific notation, put them into decimal notation so that you can figure this out and you don't make the mistake of, not knowing where your actual decimal line is. So that's an addition problem. Here's a subtraction problem showing you the same thing. 1 place past the decimal, this one goes 3 places past the decimal. Don't look at the numbers and go, oh, this one only goes 2 places past the decimal or 1 place past the decimal. I shouldn't use these numbers. You still use all your numbers, and you still just get your answer first, then trim it down. Notice how this one gets trimmed down to just 1 place past the decimal. That actually lowers the number of sig figs in the problem. We had 2 sig figs and 4 sig figs, and our answer only has 1. Don't let that worry you. That's the nature of doing these types of calculations. And that's why we want to get the same measurements all around. Can you imagine how mad somebody would be if you were part of a team, one person was getting this number and the other person was getting this number, and you did the work to get a really good number that had 3 places past the decimal and 4 sig figs, and then your partner came in and they only had 2 sig figs, and so now your answer only has 2 sig figs? Had this number also had the same number of measurements, meaning had that person who gotten that measurement used the same device or taken the time to get a more precise number, we could have had a much more precise answer. We could have kept all these numbers. That's why there's a drive to have better measurements, because then we can know more exactly, the nature of things. Okay. Sometimes you're going to get multiplication, division, and addition, subtraction problems together. So let me show you an example. Let's see. Oops. So I want this guy to not do that. Why can't I just double click with my thumb? Okay, so let's do a problem. Let's do one that maybe looks like, how about 3.489 times 5.67 minus 2.3. So the rule here is that you should always do the step in parentheses first. Okay, the step in parentheses first. And if you do the steps in parentheses first, we get 5.67 minus 2.3. We get this to be 3.37. Now, this was an addition subtraction step, right? So the rule says 1 place past the decimal is our sig figs, right? That we can keep down here. So I'm just going to note that I lost a sig fig basically in that parentheses step, because my answer can only have the number of sig figs, or at least the reported answer can only have the number of the decimal can only have the same decimal places. So 1 place past the decimal for my answer because of this number right here. Now I go back and I do my multiplication step, where I'm going to say this is a 4 sig fig number, and I'm going to treat this as a 2 sig fig number. So my answer will have 2 sig figs. You shouldn't do the math for your final answer in steps. Like, don't go, okay, now 3.489 times 3.3, because then you're going to lose numbers. So you should have just plugged all of this in, gotten your answer, and then later trimmed it down to 2. I think the answer comes out to be 11.758. So we're going to have to cut it down to right here and just say 12. Like so. Do you kind of see what I'm talking about? Okay. So that was an example. So back to some basic units of measurement. So let's talk about this. So the unit system for scientific measurements is based on the metric system. It's called the International System of Units, or we call it the SI units. There's the standard of length, which is the meter. This is defined by the distance that light travels in a vacuum. It's basically it's the distance that light travels in the vacuum in 299,792,450 of a second. So yeah, basically that's just an inverse of the speed of light. Speed of light's 299,792,458 meters per second. So in one fraction of that, that's how many meters it's gone. 1 meter. The kilogram is actually defined by a mass of a block of metal kept at the International Bureau of Weights and Measures in France. The kilometer kind of is just recently, I think, got redefined and is no longer based on a physical object, but more on a scientific constant, which is better because metals change over time. Their weights, they oxidize, they get deposits, and they even have isotopes in them that radioactively decay into lighter elements. So that happens. Temperature, of course, this is a measure of Kelvin for the SI units, but we are going to have to figure out how to get in and out of Kelvin from Celsius and Fahrenheit. And then there's time. We use the second. It's actually defined by an atomic clock as the duration of 9,192,631,770 periods. So we're going to talk about light in chapter 9, or is it chapter 7? Might be chapter 7. So 9,192,631,770 periods. So light, we say, oscillates. And depending on what frequency the light oscillates, we can say what color it is, essentially. And so the cesium atom is what we use to define the second. There's a certain electron transition that happens in the cesium-133 atom that releases a type of light. And that light, we say, when that light transitions back and forth this number of times, that's what we define 1 second as. So it's the number of oscillations of a specific type of light. Okay. So what's the difference between weight and mass? Well, the kilogram, which is a measure of mass, is different from weight. Mass is how much matter you have inside you or you're made up of, where the weight of an object is actually just the measure of the gravitational pull on the matter. So weight doesn't depend on gravity. I'm sorry, that's the opposite. Weight depends on gravity. Mass does not. In the weightlessness of outer space, you still have all the mass that you had. On the moon, you still have all your mass, but you weigh less. On the sun, you would weigh 1 billion tons or something. You'd get smashed into a little pancake because of the gravity of the earth, of the sun, but you would still have your same mass. So weight is completely different. Let's talk a little bit about SI prefix multipliers. This is important. So you basically want to choose the prefix multiplier that's most convenient for your measurement. You pick a unit similar in size or smaller than the quantity you're measuring. Like a short chemical bond, for example, is about 1.2 times 10 to the minus 10 meters. So you'd go in here and you'd find somewhere in the realm of minus 10. This is 10 to the minus 9, for example. Or 10 to the minus 12. Both of these are close. So we could say, so if I wanted to go 10 to the minus, let's say 10 to the minus 9, I could then, my decimal's in the wrong spot, so I'd have to move it over 1. Here's the problem with these, is I'd move it over 1. So now I would have a number like this, 0.12 times 10 to the minus 9, right? Because it's only moved over 9 places instead of 10 places. And then instead of saying 10 to the minus 9, I'd substitute that with nano. So I would say that this is 0.12, and we use a little n for that, nanometers. So 1.2 10 to the minus 10 meters could just be 0.12 nanometers. Let's try it another way. Let's say I have 1.2 10 to the minus 10, but I want to use this 12 number. So I got to move it over 2 more places. So 1, 2, right? So I'll have 120 times 10 to the minus 10. 10 to the minus 12. 120 times 10 to the minus 12, right? I moved it over 1. The decimal was here. and one more place that basically adds a 0. And then I replace 10 to the minus 12 with pico, and we use a p for that. So of 120 picometers. That's how this works. Now you probably know a lot of these already, since we live in the digital age, right? Kilo, mega, giga, tera. These are all terms that you would know from just storage device space, like storage space, right? Hard drive space. The ones that we use a lot are centi, milli, micro. These are 100th, 1000th, and 1 millionth. And then kilo. We use kilo a lot because we're often dealing in drugs. Chemists, I'm just kidding. Kilo is 1,000, and we use that a lot too because a gram is not very much. $1 bill weighs about 1 gram. A nickel weighs about 5 grams. In fact, you can put them on a scale and they're very, very close to that. But paper money in general weighs 1 gram. So when we think of, a cat, that's a lot of grams. And so it makes more sense to talk about things in kilograms because then we can say, oh, it's 0.5 kilograms instead of saying it's 500 grams. Again, you just pick your numbers depending on how you kind of want to talk about it. So let's talk a little bit about conversions. We need to be able to do some conversion factors, and then we'll come back and talk about density. Okay, so for most problems, we actually call this dimensional analysis. Let me write that down. Dimensional, I can't spell, that's an S. Dimensional analysis. For most conversion problems, we're given a quantity in some units and asked to convert the quantity to another unit. The calculations often take this form. So information given, conversion factor, information sought, or given unit, and then we need to use something that'll convert between a desired unit and our given unit, and then ultimately lead us to our desired unit, right? Conversion factors are what they're called. And these are constructed from any two quantities known to be equivalent. And remember I told you earlier 1 inch was defined to be 2.54 centimeters? Well, we can construct a conversion factor by dividing both sides of the equation by 1 and canceling the units. And so you can see here we divide them both by 1. If we cancel the units, we see that 2.54 is to 1 inch as 1 is to 1. Basically, these guys are equal to each other. Since 2.54 over 1 is equal to 1, then 1 over 2.54 is also equal to 1. So these two conversion factors are flip-floppable, right? We can use them upside down if we need to. And that helps us go from one unit to another. For example, if I'm given inches and I want centimeters, then I just plug in the conversion factor with inches on bottom so that my inches will cancel. Reference this up here, and this is the part of the algebra stuff, canceling units. The units will cancel, and whatever units are left on top are the ones that we'll have. And so here, centimeters will be left standing. If I'm given centimeters and asked for inches, then I plug it in so that centimeters is on bottom and inches are on top. And so a problem that looks like, 44.7 centimeters, how many inches is that? We simply plug in our conversion factor. And you guys are going to make your own conversion factors when you do the measurements lab. You're gonna measure two sides of a piece of paper. Actually, I gave you data, but you're going to calculate it, or at least see how I calculated it. But make your own conversion factor, use your own conversion factor, and actually make a conversion. Okay, so I encourage you guys to practice setting up your calculations like this. Now here is another sort of tool. We use things called solution maps. Your book uses solution maps. It's a visual outline that shows the strategic route required to solve a problem. So for a unit conversion, this focuses on the units and how to convert from one unit to another. So centimeters, inches, feet, and so that gives you an idea of what conversion factors you need to look up or figure out. The solution map for converting inches to centimeters, we already did that one. The solution map for converting centimeters to inches is just the inverse of that, or the reverse. The conversion factor for setting up inches to feet. You should all know that. 1 foot is equal to 12 inches. And so you can see a typical problem here. 194 centimeters, find out how many feet that is. And so you would be required to find these conversion factors. I'm going to give you guys a periodic table you can use for exams. And on the other side of the periodic table, you will find lots of conversion factors that you can use. But you could also Google this stuff. It's not hard to look up these factors. And then how many sig figs can we keep? Well, typically when we use conversion factors, remember exact values tend not to have those sig figs. So we would kind of be limited to what we have in our starting number. This has 3 sig figs, and so we'd want to keep 3 sig figs from our answer. And you should get in the habit of keeping only the right number of sig figs. Let's see. General problem-solving strategies would be identify the starting point. Figure out what is the given information, what was given. Figure out what you have to find. What are you after? Figure out, devise a way of getting from there to there. So setting up a solution map so that you know all the steps that you're going to have to figure out. And then you just kind of sort the information at the beginning. In a problem, you just sort the information, put all the data aside, put all the measurements aside, and kind of, if they're given values, like here's the volume, here's the temperature, here's the mass, label them so you know what they are. And then you solve it, carry out your mathematical operations, right? Pay attention to the sig fig rules, cancel units, and then check, does your answer make sense? Does it make physical sense, If the temperature of ice cream is 5 degrees and then it melts and now it's 15 degrees, does that make sense? No. Wait, yes, it does, because it got hotter, right? Yes. So that's the kind of stuff. Sorry, I was thinking of something else. But you want to check just to make sure if your answers make sense. Sometimes your conversion requires both the numerator and the denominator to get changed. So here's an example of that. Let's say that I've got 48 miles per gallon, and I want to know how many kilometers per liter that is. So the way that you do that is you tackle each conversion separately. So here's the miles and here's the kilometers, and so what I'm going to do is get a conversion factor to handle the miles per kilometer. And we would look it up, and it says that 1 mile is 1.609 kilometers. Miles cancels, and so kilometers is the only unit now on top. Now gallons we have to get rid of, and so gallons we handle with a separate conversion factor. Here we just say 1 gallon on top, is 3.785 liters. Liters on bottom. And so now both of those conversions have taken place. All the numbers are in place. We still have to do the math. 48 times 1.6 divided by 3.7. Practice that in your calculator and make sure you do get 20.4. A lot of you probably need some calculator work practice and just get used to your functions on your calculator. And so that's how you would handle a double unit like that. There are powers when converting units. Sometimes there's powers, and sometimes we have to raise our conversion factors to different powers. So for example, if we were to cube both sides to obtain a conversion factor, we wanted, let's say, centimeters cubed to inches cubed. So centimeters cubed to inches cubed is not as easy as just saying, okay, here's my, it's on top, so 1 centimeter, it would be, what is it? It would be, let me start over. I want to draw this properly. Instead of saying 1 over 2.54 and then just cubing it, right? That's not right. The units look right. Centimeters cubed looks right, inches cubed right, but this number didn't get cubed at all. So we have to cube that number also. And so here you can see that process. We would just be cubing both sides of it. Cubing not just the unit, but the number as well. So now 2.54 cubed is 16.38. Centimeters cubed, of course the unit just gets the 3 above it. 1 cubed is still 1. And so, again, check your answers. Do they make sense? And do them twice. Always do them twice. Now let's talk about density. Now density is a conversion factor. And we also, I skipped something right here, just to remind you guys, volume. We have units that are SI units, and then we also have derived units. Let's talk about derived units real quick. A derived unit is something like area or volume, right? So there's no SI unit for volume, but we do use the SI unit for length when we calculate volume. So the SI unit for length is the meter. Volume is just length times width times height, which are all measurements of length. So it would be meter times meter times meter, or meters cubed. Now we can do centimeters cubed, millimeters cubed, of course. All of these are volumes. Areas as well would be square meters, right? But we could do square feet, square yards, square inches. And so derived units come around from combining SI units. And it's also where we get, what was I going to say? I forgot what I was going to say. No worries, it'll come back to me. Okay, density. There we go. That's what I was building to. Density is also a derived unit. So there's no SI unit of density, though we use the measurement, the SI unit for mass and the SI unit for volume to deal with density. So here's a question. Why do some people pay more than $3,000 for a bicycle made of titanium, right? TI. You could get this made out of aluminum or iron for a lot less money, right? You can get it made out of rebar or something for a lot less money. Well, there's a reason. Titanium actually has less mass than steel does. What that means is, for the same amount of space, for the same size of an object, it weighs less. It's lighter. Wouldn't that be better when you're riding a bike? So we describe this property by saying that titanium is 4.5 grams per centimeter cubed, and that iron, which is not in this bike, would be more dense, 7.86 grams per centimeter cubed. So we would say titanium is less dense, and that iron is more dense. And the density here we're talking about really is the compactness of the atoms. How many atoms we can fit into a certain space. Some of this has to do with size. Some of this has to do with their nature, whether they can get charges on them or not, becoming positive or negative. But for the most part, this is just a mass to volume ratio. And so density, you can see here, is 2 units, a mass over a volume. When we want to calculate its density for solids, we often use meters cubed or centimeters cubed. For liquids, we tend to use milliliters, and I'll mention it here, that a centimeter cubed is equivalent to a milliliter. So centimeter cubed and a milliliter is the same amount of space. We tend to use this for liquids, this for solids. When we are calculating the density of a substance, you divide the mass by the volume. So for example, we could have a sample of a liquid that has a volume of 22.5 milliliters and a mass of 27.2 grams. So to find its density, we divide them. 1.21 is the math, or the numerical answer. And then the units of density are the combined unit, gram over milliliters. All right, and so in a problem, in an equation, you might be given a mass and a volume and asked to solve a density. And that's very, very easy once you know the equation, right? So let's see, we could use the density of a substance, though, to find its mass or its volume, right? We could actually even use the density of a substance as a conversion factor between mass and volume. So, for example, let me show you. If we used, we can even use this one right here, this liquid that we used in this problem. So let's say I have, 68.4 grams of this stuff. 68.4 grams of this liquid. And I want to know what volume I need to measure out, or what volume that takes up. Let's say that's my question. is I want to know how much volume is taken up by the 68.4 grams of my stuff. Well, the units of density are set up to actually be a conversion factor. So I just multiply it in a way that grams cancels. So I'll put grams down here, and I'll put milliliters up here. Now, the density is telling me how many grams there are per mils. So there's the 1.21 that goes on the bottom per 1 milliliter. And then I'd get my calculator and I'd do the math. And our answer would simply have milliliters in it, right? And we can do that. I think I have another example, actually. Maybe we can do another example. What about if we didn't use this number? I don't know what that number would be. Let's see. It would be something bigger than 51.8. It's going to be like, I don't know. It's between 50 and 60. Here. Sorry, my key that I had going in, I used a different number. I used 1.32 for some reason instead of the number that I had shown here. So if we do this, just so you can see, what if we wanted this answer in centimeters cubed, right? What if we wanted to convert it to centimeters cubed? No big deal. We could also stick in here 1 mil is 1 centimeters cubed. And then everything would cancel out. The grams would cancel, the mils would cancel. I think 64.8 with this number comes out to be 51.8. So you can check your math along with that. So 68.4 grams would be 51.8 centimeters cubed if we were looking for that number, the volume. So we can use density as a way to convert. Now, density can also be used as a way to identify a substance. Like if we know the density, but we don't know what the object is. There's a famous sort of story about a king who instructed Archimedes, I think it was Archimedes, to figure out how to tell if his crown was real gold or if it was something to do with the crown and the gold. And he was having a hard time measuring the accurate measurements of the crown to get the density, because they could figure out, gold is supposed to be 19.3 grams per centimeter cube, but he couldn't measure the crown very accurately. And so the story goes, Archimedes gets into this bathtub, right? It's a bathtub. He's like, his legs. And he gets in the bathtub, and the water level rose, right? Here was the water, and then it rose higher, right, by some amount. Let's call it dV, delta volume. And then he said, Eureka! I figured it out. And what he figured out was that he can measure volume by something called displacement. And you guys are going to, I keep saying that because I'm stuck in a world where we go to labs, but you're going to watch how this is done on a video and not do it in person. But displacement is how we can get the volume of an irregularly shaped object. If we submerge it in water and we keep track of where the initial water was and the final water is, we can figure out the exact volume of a weird shaped object. And so that's what Archimedes was able to do. He could weigh it, he could get the volume of it, and then he could find out if it was really gold or if it was not gold. All right, and it actually came up in an issue, in a real life thing, in 1999. NASA lost a lot of money because two different groups were working in two different units, and they didn't communicate to each other what their units were. And so then the orbiter descended too far into the Martian atmosphere. This was an orbiter going to Mars, and it burned up. And so you can actually do the math on this if you guys are interested in it. You can try the calculations here. So suppose the Mars orbiter was to have established an orbit at 155 kilometers, and that one of the group's engineers specified the distance as 155.10 to the 5 meters. Now, the next group thought that was feet, so they put it in as 1.55 10 to the 5 feet. What's the actual difference in kilometers? And so if you guys are interested in kind of calculating that, I can check your answer, or we can do it together in the next video. But give that one a shot. I think that would be nice for you guys to practice. Find out how low the orbiter actually went. So it was supposed to come down. Here's a satellite or whatever, boop, boop. And it's supposed to be above the Earth by 1.55 10 to the 5 meters. So 1.55 10 to the 5 meters above Mars's surface. Find out what the difference is when someone programs it at 1.55 10 to the 5 feet. Okay. Learning objectives for this chapter. I've listed them out here for you guys. Hopefully this helps. I will do this at the end of every chapter. Make sure to go over these learning objectives. This is where you should focus your effort on the homework or on practice problems. If you're doing all the homework and that's not enough, focus on the practice problems. Expressing numbers, using the right number of sig figs, figuring out how many sig figs a number has, being able to round the right number of sig figs, doing the calculations of sig figs, multiplication and division, subtraction and addition, and also the combination type problems. And then converting between units, both when they're in the numerator and the denominator, or if they're raised to a power. Using density as a conversion factor and calculating it. This will never go away. We will do this all semester long, using density. So get in the habit of it now. All right, guys, that was it. So I will see you in a video tomorrow.